Hello everyone, it has been a while since I did anything related to backtesting of trading strategies, and was looking at some recent blog post that was published in November 26, 2019 by David Varadi. He usually has some brilliant ideas, and while looking at it I realized that there are some similar strategies that I'd like to test lately, and was thinking that it might be a good idea to take this one as a start and reproduce it in my framework. So on my blog for a long time I have been using R to do backtesting, but for the past couple of years I have switched to Python mostly. And in Python I'm not that familiar actually how to do some of these things. I use, for example, for this strategy you need to get the data from Yahoo, then to compute moving averages and all these things, and I decided to do this one in Python for my own education. So the blog post, you can find it here. The strategy is showing how to use an adaptive moving average instead of the regular moving average, and it shows the performance of the strategy of the 200-day moving average crossover and the same strategy but using the adaptive moving average and a small table. So let's do that in Python. So to do that in Python, I decided to use a Google Colab notebook, which you can see here. I mean, this is really cool. And the first thing in the notebook is to install some packages that we need. So I'm installing here the Pyfolio package. The Pyfolio package is a package created by Quintuitive. Quintuitive is a company that does a lot of you can actually backtest strategies on their website, and you can do research in notebooks and stuff like that. I have used them, it's pretty good. So I'm going to use this package and it needs to be installed. Now the reason I'm installing it directly from GitHub is because there is a bug in the package which is available in pip, and this bug is fixed in the main branch as of late, but hasn't made it to pip yet. So I'm using the package directly from GitHub, and as you can see, the Google Colab notebook had no problem installing the package. Let me clear the output. So then we'll just load the packages that we need. The empirical package is another statistical package that comes from the Quintuitive folks, and we load what we need. The pandas data frame package is to download the data. So let's go and get our data into this SPY variable. So this is using the pandas data reader data, and it obtains the SPY from the beginning. So let's pull it here. Done. Now this is our function to compute the moving average, the 200-day moving average. It's very simple. It's basically just does the rolling pandas function directly and assigns names to the time series index and to the time series data. Okay, and the last one is basically to prepare the data for the next operation. So we compute the SMA calling the function, then we concatenate the closing prices of the SPY. We concatenate them with the moving average, and we assign names to those columns. So let's do that. And the last step is where we actually call the backtesting, which is the Pyfolio. So what is the idea here? The idea is that based on the SMA, on the moving average, we will compute our position. So our position is either 0, which means out of the market, or it's 1, which means long position. So out of the market, we have to handle the special cases when we don't have data in the beginning of the series, when the moving average, it's a 200-day moving average, so the first 200 days are actually non values. So for those, we want to compute the position is 0. The only time when we want to compute the position as 1 is when we do have values for both the prices and for the MA, and the prices, the close, is greater or equal, the opposite of this one, to the moving average. So that's how we'll compute our positions, right? So that's the signal. So the signal is a time series that is 0 or 1, depending on the position that we hold. Now, once we compute the signal, what we need to do is to multiply the signal by the returns. So the returns actually, you can see something interesting here. So because we are pulling out the data from Yahoo, we have the open, high, low, close, volume, and the adjusted close. So what is the adjusted close? The adjusted close takes care of if there are stock splits, but in our case, with the SPY, the important part is it also takes care of dividends. So when we compute the returns, we want to use the time series with the dividends. But when we compute the signal, it's usually better to use the actual return of the day, not adjusted for dividends, because it's more realistic. So you can see here, actually, I'm using the close, the actual close, when computing the moving average, and I'm using the returns. For the returns, I'm using the adjusted close, which is adjusted for dividends. So now we have one column which gives us the position, this is the signal, and we have one column which contains the returns. Now, when the signal is 0, we multiply 0 by the return, and we get a return of 0 for the strategy for this day. When the signal is 1, we have a long position. We multiply the return by 1 by the return, so the strategy actually has a positive or negative return for that day. Now we have to shift the signal by 1, and the reason for that is that let's say at the close today we computed the signal and we got a 1. We take the position, but this 1 does not apply to the return of today, it applies to the return of tomorrow, because today we are just taking the position at the close, so the return is, we are still 0 in terms of how much return we have for the day. So that's why, to align the signal with the return, we have to shift it by 1. This is common practice. I'm just trying to cover the steps in a little bit more details here. And now we have a data frame which has those two columns. So then we compute the daily returns of the strategy by multiplying the return columns by the position column, and we are replacing in the positions all the NAs, nuns, with 0. So 0 position when we don't have anything else. And we set up the names. And finally, we take this interval of the daily returns, we save it for later because we will use the strategy for later, and we call the PyFolio create full tier sheet, which creates a lot of statistics of a trading strategy. So I'll just run this and you will see what happens. So it starts with the PyFolio computes lots of things, it's still computing, but what it starts with is actually the returns. So we get the annual return 6922, some cumulative returns, Sharpe ratio, Kalman ratio, and so on. Then it continues more statistics, and then it starts creating those charts. Okay, so let's just go quickly through them. So this is actually on a logarithmic scale. And now if we go back to our article, well, isn't that chart similar to the orange line actually? This is exactly the orange line actually, literally in the chart. And if you look at the return, the 200-day moving average strategy showed 7.4 annualized return with a maximum drawdown of 28%. And here we get pretty much the same on the statistics. We get 6.92% annual return and the maximum drawdown of 27%. So at this point it's pretty clear that we can claim that we have computed everything properly. So this was just to warm things up. Now let's move to the actual adaptive moving average. So the formula for the adaptive moving average is actually over here, outlined over here. And what this does is basically implements the formula. So there are a few things. First, we have to compute the volatility, and the volatility is computed from the returns using a moving average of the returns. So I'll use 25 days as a moving average of the returns. And yeah, and actually we want to compute the standard deviation, but the standard deviation when we talk about financial asset returns, it's a little bit different, because the standard deviation formula over a short period of time, so that's what we're trying to compute. This is the formula that we're trying to compute. But notice something else. X is actually the mean. But the mean, we know, the mean for the last 25 days or so is probably not zero. But we know that over a long period of time, the actual mean is also zero. So what I have here, STD0, is basically this formula assuming that the mean is actually zero. So it's actually x to the power of 2, because this is 0, and you can see this computation. Anyways, this is not important. You can do it both ways. That's how I did it for some other reasons. So once we have the standard deviation, which is called vola here, we have to compute, as David Varadi explains, we have to compute the ranking, the percent rank function over the series using an expanding window, minimum ranking period, and so on. So stats rank data will do that. Then we have the two constants. The two constants are directly from the paper. So SC equals 0.75 and the other one. And then we copied the series. I wanted to return the alpha when I was testing whether it's computing properly, and we do exactly that computation. So here is actually the formula computed, a little bit massaging to make sure that the alpha is between 0 and 1, and so on. So this is actually the formula. We can run this. And the last thing is to actually compute the everything. So we will say that, so we're going to pass to start it right away and explain. So we compute the adaptive moving average, and we compute the 200-day moving average. So why do we do that? Because I was having a lot of problems reproducing it until I noticed in one of the comments that actually to determine the signal we have to compare the adaptive moving average versus the slow moving average, the 200-day moving average. If we don't do that, what happens is the new moving average, actually, the new moving average, as you can see, the orange line here and the blue, is actually very close to the price. So actually we'll end up with many more trades and it's not going to be as good. So what we're comparing literally for the signal is we're comparing the orange line here with the slow 200-day moving average. Whenever we are above, we buy. Whenever we go below, we sell. So this is how the smoothing happens. And now remember this picture. So here are the results of the so we get 9.7. So there is a difference in my result compared to this table, but actually it's very close. It's very close. and you can see that the maximum drawdown is only 20% now, and you can see the maximum drawdown is 19%, which is exactly the same. Not only that, when we code the PyFolio create full tier sheet, which creates all these statistics, we specified that the benchmark that we want to compare against are the returns from the previous the backtesting of the previous strategy. And when we go here, ta-da, this is actually exactly the same picture, or very similar to what we see here, right? So here is on a log scale, here is on a log scale, and the statistics are pretty much the same. And a lot of stuff from PyFolio. You have the month-by-month return and all this thing. The reason I wanted to show you that is I'm really impressed, once you get used to PyFolio, how quickly one can do that stuff. Back in the day, and you can see that on my blog before, back in the day, we had like R packages that we were creating and basically having these hit charts for month by month, annual returns, and all other things added. Right now you have all of that in a single line of code coming from PyFolio. I mean, this is really impressive, and my whole experience with Collapse and the Google Collapse and the backtesting in Python has been just awesome. And last, before I go, this is one way actually to backtest stuff. In my general experience, there are two ways. One is what I call vectorized. This is the vectorized, and the reason I call it vectorized is because here what we do, we take our returns, we multiply it by the strategy's signal, and we get the backtest. This is applicable to any strategy for which the current position doesn't depend on the state. So at any point, just based on the signal, I know whether I'm gonna take the position or not. And this is very fast approach, and it's good to have it in your tool set, because the other one is more expensive. The other one is like what is implemented in this beautiful package called Backtrader in Python. That's what I use lately. There are other ones, but this is so-called event-based backtesting. So the idea here is that you declare your strategy and you have a method. This is just showing an indicator. But you have a method in your strategy which is called by the framework for every single day of trading. So it's like real trading. This is like more realistic, and you can implement more sophisticated strategies. On the downside though, if I had to implement this strategy, which I just show you, if I had to implement it this way, I had to do a few things. I had to create a new strategy class. I had to do I had to implement two indicators. Probably the SMA indicator is already there, but I had to implement the adaptive moving average indicator, and then I had to run the whole thing and then do this visualization. And by the way, they also support integration with PyFolio. Well, you can see how simple the code is if you know what you're doing in the vectorized. So I'd rather use the vectorized approach for for quick analysis like that, and then for everything else I usually use the Backtrader platform, but that's for another post. That was for today. I hope you enjoyed, and have a great day.